Hello everyone, I'm Zhenbin Li. Today I'd like to introduce the fundamentals and the industry development of SRv6, short for segment routing over IPv6. First, let's look at the segment routing technology, which was proposed in 2013. Leveraging the source routing mechanism, this technology uses segments to represent links and nodes on the network. In the MPR's forwarding plane, segments are represented using labels. In this case, some labels represent specific nodes, whereas other labels represent specific links. We can use the label stack to identify a data forwarding path that needs to traverse specific nodes or links. This label stack consists of a group of labels representing the nodes or links and is called an SR path. Each SR path is generated on the ingress to direct packets to the specific nodes or links. This is the basic implementation of segment routing. Segment routing offers the following benefits. First, it replaces conventional protocols such as MPR's LDP and SRv6, reducing the number of required protocols. Second, it offers great scalability. Traditionally, SRv6 signaling is transmitted in soft state mode to support MPR's traffic engineering, leading to poor scalability. In contrast, segment routing only requires the ingress to maintain SR path states. This not only reduces the number of network states to be maintained, but also improves the scalability of MPR's path. Third, because segments represent different functions, paths generated based on segments are highly programmable, meeting the service quality requirements for different services. And fourth, segment routing allows faster rerouting to achieve 100% coverage on any network, enhance FR, deployability, and service reliability. Segment routing supports two types of forwarding planes. During the initial stage of segment routing developments, SRMPRs was predominant. As SRMPR standards have matured, people are focusing more on SRv6, which use the IPv6 forwarding plane. Currently, SRv6 is becoming a hot topic in the industry. As essential elements in SRv6, SRv6 segments are 128-bit long, which is the same as the IPv6 address length. Typically, an SRv6 segment consists of three parts. The first part is the locator, which is equivalent to an IP address. This enables SRv6 to inherit the routability of native IPv6 addresses so that traffic can be forwarded according to the specified locator. The second part is called function. We can use a function ID to identify specific services that cannot be represented using addresses, such as VPN instances. MPRS use labels to identify VPN instances. As such, a function ID is somewhat similar to an MPRS label. In addition to identify a VPN instance, a function ID can also identify the instance of other types of services. The third part is the optional arguments field, which carries variables used to instruct packet forwarding. These are the basics about SRv6 segments. SRv6 combines different segments into a segment list to form an SRv6 path. Typically, SRv6 path data is encapsulated in a specific SRv6 extension header, which is called an SRh, short for segment routing header. The segment list in an SRh identifies a complete SRv6 path. SRv6 supports two working modes. One is called BE, short for best effort, and it is similar to LDP in MPLS. The other is SRv6 traffic engineering, which is similar to MPLS TE in MPLS. Now, let's look at an example to understand how SRv6BE is implemented. On this network, L3 VPN is configured on both the ingress and egress PEs, and a VPN ID is configured for the VPN instance on the egress PE. This VPN ID is a 128-bit SRv6 segment, of which the first part is the locator, A2 column 1, and the second part is the function ID, B100. It's used to specify a local VPN instance. In this example, BGP advertises the VPN ID of the corresponding route from the egress PE to the ingress PE. As such, the ingress PE obtains the VPN ID. After receiving a packet, the ingress PE performs SRv6 BE encapsulation and sets the destination address of the packet to A2 column 1 column B100. During intra-domain packet forwarding, the ingress PE only needs to search for the routing entry matching the prefix A2 column 1 according to the longest match rule, and then forward the packet to the egress PE hop by hop over the shortest path. After receiving the packet, the egress PE gets the corresponding the VPN route table according to the function ID B100 in the VPN ID, then searches for the route and forward the packet to the corresponding CE. In this process, the packet traverses the entire SRv6 domain through only IPv6 route-based forwarding. As such, we call this mode SRv6BE. Next, let's see how SRv6TE is implemented. In this example, although VPN is also configured on the ingress and egress PEs, there are specific requirements for the forwarding path. Assume that a packet needs to traverse two specified nodes. One is A1 column 2 and the other is A1 column 3. After the ingress PE obtains the specified VPN ID, it needs to include the SRv6 nodes A1 column 2 and A1 column 3 in the SRv6 path to be generated. To achieve this, the ingress PE encapsulates the packet with an SRv6 header, which carries an SRv6 segment list covering A1 column 2, A1 column 3, and A2 column 1, column B100. This segment list specifies that the packet need to pass through nodes A1 column 2 and A1 column 3 on the SRv6 path to reach the egress PE A2 column 1. On the egress PE A2 column 1, the function ID B100 in the VPN ID indicates the corresponding VPN routing table. During the forwarding process, firstly, the destination address in the IPv6 header is set to A1 column 2, thereby directing the packet from the ingress PE to A1 column 2. After the packet reaches A1 column 2, the pointer of the segment list moves downward so that the destination address is changed from A1 column 2 to A1 column 3 to direct the packet to A1 column 3 through a route. Similarly, after the packet reaches A1 column 3, the pointer points to A2 column 1, column B100, which is used as the new destination address in the IPv6 header. According to the locator A2 column 1 in the destination address, the packet is directed to the egress PE A2 column 1 through a route. Then, according to the function ID B100, the egress PE gets the corresponding VPN routing table, then search for the matching route and forwards the packet to the corresponding CE through the route. This is how SRv6 TE works. From this process, we can see that a segment list indicates a specific path is used in the SRh in order to meet specific constraints and service quality requirements. The implementation mechanism of SRv6 TE is different from that of SRMPRS. In SRMPRS, the top label is removed each time the packet arrives at the specified node. In SRv6 TE, however, the segment list is reserved during the forwarding process, enable the egress PE to obtain a complete segment list based on which the SRv6 path used for packet forwarding can be determined. In contrast to MPRS and SRMPRS, SRv6 has the following advantages. The first advantage is its backward compatibility. SRv6 segments retain locators, meaning that root attributes are kept so that SRv6 is compatible with IPv6 forwarding. As such, SRv6 incapable nodes can use IPv6 routes to forward packets and enable them to traverse SRv6 incapable nodes. This ensures compatibility with existing IPv6 networks and facilitates incremental service deployment and evolution. The second advantage is simplified inter-AS implementation. In MPRS, because multiple AS supports MPRS, establishing an end-to-end MPRS path typically requires the use of complex inter-AS VPN technologies such as option A, option B, and option C. This means that many MPRS labels need to be advertised through signaling in the establishment process, complicating end-to-end MPRS path establishment and service deployment. In contrast, because SRv6 is compatible with IPv6 forwarding, IPv6 routes can be used to forward packets across different ASICs, facilitating end-to-end path establishment in inter-AS scenarios. As such, SRv6 simplifies inter-AS implementation. In addition, SRv6 offers high scalability. In inter-AS scenarios, MPRS label need to be bound to routes in one-to-one mode. This means the number of required labels must be the same as that of destination routes, limiting the degree of scalability. With the SRv6, locator can be aggregated due to their route attributes. By aggregating routes for a specific destination address, device can aggregate multiple route forwarding entries into one, thereby reducing the number of entries and improving network scalability. The third advantage is excellent programmability. SRv6 provides a three-dimensional programming space to offer higher programmability than SRMPRS. First, multiple segments are flexibly combined into an ordered segment list to implement programming. Second, each 128-bit SRv6 segment can be flexibly partitioned to support more functions. And third, the optional TRAs in the SRh can be used to encapsulate irregular and variable length forwarding information, facilitating new functions on the network. SRMPRS lack all these advantages, particularly the last two. As such, SRv6 offers far superior network programmability compared with SRMPRS. The last advantage I want to mention is that SRv6 facilitates end-to-end deployment. A network is typically divided into multiple domains, and different technologies may be deployed on some networks, making the network more fragmented. For example, some data centers often use the VXLAN technology, whereas the one often use the MPLS technology. This requires complex gateway functions to be deployed in order to implement mutual mapping, thereby achieving service deployment across these different networks. In this case, due to the IP reachability of SRv6, we can use SRv6 as an alternative to VXLAN to some extent. By deploying SRv6 in both the data centers and WAN, we can establish an end-to-end SRv6 path across these networks, simplifying network service deployment and supporting cloud network synergy. As we reach the end of this video, I'd like to briefly introduce the development of the SRv6 industry. In terms of standards maturity, SRv6 standards were proposed in 2017 and have become relatively mature after several years of development. The two most important drafts, the framework of SRv6 network programming and the SRh encapsulation on the forwarding plane, have been released as the RFC, that is, the formal IETF standards. The drafts regarding the extensions of IGP, BGP, VPN, PCEP, and other protocols related to basic SRv6 features have been adopted as working group drafts and almost stable for a long time. They will also be published as the RFC soon. This means that standards for basic SRv6 features are quite mature. In terms of product support, vendors including Huawei and Cisco have released multiple commercial products that can support SRv6. In addition to some open source software such as Linux, many testers and chipsets also support SRv6. This indicates that SRv6 has gained wide acceptance. In terms of interoperability test, the ENTC, short for European Advanced Networking Test Center, has conducted multiple SRv6 interoperability tests since 2019, covering the product of Huawei, Cisco, and many other vendors. SRv6BE, SRv6 VPN, and other SRv6 features all gain good test results. Finally, in terms of commercial deployment, the industry's first SRv6 site was deployed for China Telecom Sichuan in January 2019. Since then, the sites of multiple customers, including SoftBank, China Unicom, China Mobile, and Bank of China, etc., have adopted SRv6. Statistics show that SRv6 has been deployed at more than 100 sites, enabling SRv6 maturity to be fully verified. In the future, we believe that there will be more commercial deployment and application scenarios covering backbone, metro, and mobile transport networks. SRv6 can play a big part in transporting services on such networks. In general, with the growing maturity of SRv6, the SRv6 technology will be further developed and deployed for commercial use.